Joachim is from Germany, but he lived for most of his youth in Singapore, until when he decided to trade Kaya Toast and Singlish for German and Schäufele, and moved to Germany to study computer science. In his university, he learned how to write code for ARM and was able to actually make use of that knowledge right on time for the new Macs to come out. So the talk is implementing a ARM backend for stage 2. Joachim, the stream is yours.
Hello, everyone, and welcome to an ARM backend for the stage2 Zig compiler. As Loris already introduced me, I'm Joachim Schmidt, and I have some more. If you can't pronounce my name, if you have trouble, then you can just call me Joe. That shouldn't be a problem. I study at the moment in the Technische Universität Darmstadt. Like 3 semesters ago, I had a course which was about ARM assembly programming, and I decided to use that knowledge in practice and write an ARM backend for the Zig compiler. So first, an overview of some main things I'll be talking about today. First, I'll explain what compiler backends and what stage 2 and that stuff actually means, what that actually is. And then I'll go on to describe the ARM architecture, like only a little bit. Only some major details of it. Just for clarification, I'll be discussing the ARM 32-bit, like the RA32-bit instruction set, like not the 64-bit, which is similar but also has some major differences. And then finally, I'll do a live demo on a Raspberry Pi, which I have here. I don't know if you can see it. Yeah. I hope it doesn't. The SSH still works when I'm doing that. And then I'll do a Q&A, as with every other talk. So what is a compiler actually? A compiler is just a program that converts one description of behavior into another description of behavior. And that process is called compiling. So let's look at a basic Hello World example. We have some C code, and we use GCC to compile that to an executable. Note here that you can also use LLVM, but A, I can draw a dragon, and B, I didn't have enough RAM for that, so I have to look into that. So how does it look like in Zig? We have a Hello World Zig file, which is the goal of this presentation. We want to compile that for ARM, and we use the Zig compiler, and we get an executable. But where does this Zig compiler come from? I mean, it can't jump out of thin air. I mean, it has to go through that same process to be a real executable. So this is where the bootstrapping process of Zig comes into play. So at the current time, we have one code base, which is called Zig stage 1, and we use a C++ compiler, such as GCC or LLVM, to compile that to an executable. And we call this Zig stage 1, actually Zig stage 0, but I'll just abstract over these differences. After that, we have the Zig self-hosted compiler, which is called the Zig stage 2 compiler. And this is the Zig compiler written in Zig. So just for the explanation of the colors here, I'll use red for C++ code, blue you have seen blue for C code, and green for just executables. So we use this stage 1 compiler to compile the Zig self-hosted compiler, which is written in Zig, to Zig stage 2 executable. And what we want to do after that, the current plan, is to have just one code base, namely the Zig compiler written in Zig, use the Zig compiler to generate C code, and then use a C compiler to get this compiler. But as you can see here, this is not exactly technically the same as bootstrapping, because we have a kind of recursive dependency here. We are using the Zig compiler here, but we only get it down here. So the solution to this, is which is also the plan Andrew has, is to separate this, the C code, and into another code base. So we have two code bases. One, the Zig compiler written in Zig, and one, the Zig compiler, which was originally generated from Zig code and is now C code, but maintained on its own. And then we have the normal bootstrapping again. So, and now let's talk about backends. We have our hello world Zig file, and we want to compile that to an executable. That's okay. But there are different executable formats. If I compile something on my machine, which is an x86-64 machine, and it produces a hello world executable, which is for the x86-64 instruction set, I cannot run that on, let's say, an ARM CPU or a MIPS CPU or any other kind of CPU which is not x86-64. So here is where the concept of a backend comes into play. So the Zig compiler can also generate from the same hello world file a executable for the ARM instruction set. And I'll use pink for the color of the ARM instruction set. So this is what you already have seen, just to annotate this in preparation for another concept called cross-compiling. So we can also use the Zig compiler in another architecture and compile, for example, for my architecture on my laptop. So this is called cross-compiling. So I have the Zig compiler, which is running on my CPU, on the Raspberry Pi, for example, which is an ARM CPU, and it's compiling for a target that is not native. Like, it compiles a program that the CPU itself cannot run, but it still can compile this. And this is what we are trying to achieve with the stage2 compiler. So before I'll delve a bit into the ARM architecture, I'll talk a bit about the general architecture of computers. Most computers nowadays, if you generalize all the details away, are following the von Neumann architecture. And that means we have a CPU and memory, and this memory contains instructions as well as data. So in detail, this means this memory contains some instructions, like what these instructions mean. I will I will delve into that later, but it contains instructions as well as data, which means I can load, for example, this into a register on my CPU, but I can also load an instruction. It's because it's from the same memory. I can just access it, instructions and data as if they were the same thing. And my CPU contains registers, that is an important part, which are very small amounts of memory, which the CPU can access instantly, well, almost instantly. And we have for example, an arithmetic logic unit, which performs stuff like addition or subtraction or bitwise operations. Yeah, and of course, other stuff in the CPU. CPU is not that simple, but we'll keep it at this. So, and ARM is, in contrast to many other instruction sets, is a RISC. And to understand the concept of RISC, I'll contrast that with a CISC. And CISC stands for Complex Instruction Set Computer. And architectures that are CISC have some properties that the RISC architectures do not have. For example, one of these is that if I compile this very small function without optimizations for x86-64, which is running my laptop, and this is a CISC instruction set. And for example, if I compile this addition, it gets compiled to this. And what we can notice here is that we have one operand, which is a register, but another operand, which is a memory location. This is like a pointer to a location in the current stack. So this means we can, as operands for an arithmetic instruction, we can have as well locations in the memory, which is something which is not possible in a RISC architecture like ARM, for example. Here we can see the add instruction can only access registers. This is the register where the location is saved. This is the first operand. This is the second operand. So this means in R0, we will save the sum of R0 and R1. And you can see here, before we can do that, we need to load all these first. So we need to first, of course, this is compiled without optimization. So these stores and this store are technically dead stores. But the essence is that we need to store them into memory and then load them again. And this we cannot do this without loading. So in the CISC architecture, we only need to load it once and get the other operand from the memory. But in RISC, we cannot do that. So this is one property from RISC, and RISC also have RISC instruction sets also have many different properties which differentiate them from CISC, but I won't go into detail there. So some few examples of the main instructions we encounter in the ARM instruction set, which are used in every program, basically. We have data processing instructions, which are additions and subtractions and just moving, negation, and all those other stuff that operates on registers. Then we have memory instructions, which are like which load and store registers into memory, and we have branching instructions. So without branching instructions, we don't have like real control flow. We cannot do if statements or for loops or while loops. We can only do these with branches, which mean this branch, for example, is a branch with an offset, which means I can jump higher into the code or lower into the code, and this is an indirect jump. So I jump into the address which is specified in a register at the moment. And briefly, I'll show you for example, for the add instruction, the actual representation in the binary file, which is a 32-bit integer here stored in a big endian way. But the essence is that these operands are saved into the memory locations here. So this is destination register, RD, which is saved here. So this will be 0, 0, 0, 0. This is the first operand, which will be saved here. So 0, 0, 0, 1. And this is the immediate value, which will be stored here. Yeah. So, yeah. Maybe one special thing about ARM which many other instruction sets do not have. I don't know if any other instruction set does have this feature, but ARM has the ability to conditionally execute every instruction. So every instruction in the ARM instruction set, in the A32 instruction set, has a condition, which means for small if statements or for small code that is conditionally executed, we do not have to have a branch. We can just linearly go through the code and just pick out those instructions which we want to execute and just don't execute those which we don't want. So, for example, this function can be compiled without any conditional branch. This is very important for CPUs that do not have a branch predictor. Some ARM CPUs, in fact, do not have a branch predictor, and this is very useful for them, as this speeds up the code considerably. I look forward to implementing this feature in the Zig self-hosted compiler, but we'll see how that goes. Because at the moment, conditional branches are not yet implemented. Now we'll have a quick live demo on a Raspberry Pi. But before that, I'll show you a bit the code, which actually powers this backend. So this is the codegen.zig file. This is where all the code generation stuff happens. We have stuff which is, we have this generic function struct, which is generic on the current or on the target CPU architecture, because we can cross-compile. And this struct has many different functions, depending on what we want to do. So, for example, we can generate a return. We then switch on the architecture. For example, if we want x86 or x86-64, and on ARM we do this. Like this is, and we also have to do because this is still a work in progress, this backend. But we also have larger functions such as setreg, which set a register with a value. And you can see here's the ARM switch. And we can set this with, for example, an immediate value or with a register. So we copy one register into another register, or we copy the contents of a memory address into a register and stuff like this. So, and we also have the codegen ARM file, which is ARM specific. This is specific for the ARM instruction set. We have a enum, which can represent all the different condition codes that an instruction has. We have another enum for all the registers that are present in the ARM instruction set. And we have a big tagged union for instructions. Of course, this is not complete yet, but we have the main things here, like data processing, which is a packed struct. So we can directly, once packed structs are 100% complete, we can directly just bitcast this into the 32-bit integer that we are going to write. I can show this. For example, here, when we write a move from one register to another register, we can write this to U32. So this is a integer, and we write that directly to the code. And as you can see here, we have this instruction.move. And we can skip here and look at that. The move instruction just has one register, one operand, because you can also move immediates. And this goes to data processing. And data processing is like kind of the helper function which returns this instruction with the tag type data processing. Yeah. And then finally, we call the toU32 function, which has this horrible thing here because, yeah, as I said, packed structs don't work completely yet. Yeah, so yeah, this is a short overview of the code. Yeah, for every instruction I currently support, there is a special function, and also for like alias instructions. These are more complicated things, like for the pop and the push instruction, because they aren't real instructions, they're like pseudo instructions, and they change depending on how many arguments there are. And I use the Zig language feature of having like pseudo var args and like anonymous structs, and depending on the size of the struct, output a different instruction. Yeah, let's have a quick demo of the code on the Raspberry Pi. So this is currently my Raspberry Pi, just to prove. Yeah, it's running a ARM 1176 CPU. It's the Raspberry Pi model B Plus version 1.2. And yeah, I already have, let's look at the code. Yeah. Yeah, let's have a quick look at the code. Yeah, as we have no import support in stage 2 yet, we have to define the start function ourselves. Like, we can't do the normal Zig way of saying import std and then main void, because this requires the standard library, and we can't do that yet. And also the std.debug.warn or get stdio and then print or write doesn't work because we don't have the standard library yet. So what we have to do is we have to write everything ourselves. So I call a print function first. This print function has an assembler instruction, an inline assembler instruction for the literally the syscall into the Linux kernel to print hello world. Of course, once we have the standard library, we don't need this anymore. And the exit function, also like a quick demo of parameters. So parameters actually work. Not fully yet, but simple parameters, like if I just want to pass in one U32, this will work, and I can just set the exit code with this parameter. So yeah, I think I have the executable here. So let's remove this. Yeah, I cross-compiled the Zig binary here. This is I compiled this from my machine and copied it to my Raspberry Pi, because I thought it may take a bit too long to compile the Zig compiler in C++ on a Raspberry Pi and then also compile the Salesforce compiler. So I just cross-compiled it and copied it into there. Yeah, so this should now be able to compile this hello world Zig file. So this is this ZIG binary is fully self-hosted. It doesn't have LLVM extensions, so it cannot detect which kind of CPU my Raspberry Pi is currently running, because ARM architectures have different versions, and depending on the version, some features work, some features don't. Like, for example, in here we have the move wide instruction, which moves a 16-bit unsigned integer into a register. This is not supported on my Raspberry Pi. So the compiler needs to know if the CPU actually supports this instruction, because if it doesn't, it can't can't possibly run the file. So I'll have to specify the target manually. Yeah, I'll just choose ARM native. And yeah, we have our hello world file.
Joachim, don't forget that your webcam is covering the bottom left part of your screen.
Oh, yeah. Oh, yeah. Then just...
That works. Thank you very much.
I never use the tiling window manager features anyway, so... yeah. So, and it works. Yay. Yeah, and we can also demo a bit of the incremental compilation here. Update. For example, we can change exit code. I want to exit with 1. Can't format. And call update again. Okay, and then I'll open another shell. And call hello. And I'll do this with fish. And you can see the exit code is 1. And we can also change the string. And yeah. No. Pressing the wrong buttons. So, yeah, this incremental compilation feature is really cool. I can just update here, and it just updates. Yeah, this is a short demo of what the stage2 compiler is currently already capable of doing on the ARM backend. And of course, this is not nearly the whole SIG language. Loops are not supported yet. Conditional branches are not supported yet. Yeah, imports are not supported yet. So yeah, we have a lot to look forward to in the SIG self-hosted compiler, which I find really, really interesting, and it's really exciting to be a part of that. Yeah. And yeah, that was it. And yeah, I'm looking forward to questions and answers.
Awesome. Thank you very much. The demo was very nice. So it's self-hosted compiler with incremental compilation on a Raspberry Pi.
Yeah, this I can show you the hack I did to compile the because if I compile the ZIG self-hosted compiler with a ZIG build, it doesn't actually register that my CPU on my Raspberry Pi is an ARM 1167 something, and that's why I modified the build ZIG to hard code my CPU here so that it works. But apart from that, yes, I just ran ZIG build, copied the binary from the ZIG cache, and then yeah, it just works on the Raspberry Pi. Yeah.
Awesome. Wow. Okay, so while people start thinking about questions for you, let me start with the default question. So how and when did you discover Zig?
This is kind of a long story. So in the first semester of university, we had first before even the semester started, we had a so-called Orientierungswoche. So where all new students of the computer science faculty are gathered, and we learn about the university and how stuff works.
So like
And there was
like an open day.
yeah, I don't know how it's called in English, but yeah.
Okay.
And there was one guy who really inspired me because he said that we should learn as many programming languages as possible, because you kind of if you are stuck with one programming language, your brain starts only thinking like that programming language, and you have more programming languages in your repertoire. You have like more methods of thinking about problems, and I started doing that after the first semester with NIM, which is somewhat similar to Zig. And I even wrote like a pretty non-trivial program in NIM. And if you discover NIM, I think you basically also discover Zig. And yeah, that's when I discovered Zig, and I've been following it ever since. And yeah.
I see. Awesome. Okay, let's see if anybody has questions. So some people were asking before about stage 2. So like if somebody wants to try out incremental compilation, not necessarily on the Raspberry Pi, but like on their normal machine. So we can assume 8664.
Yeah.
What do they have to do?
The stage2 compiler already has some tests. People can try these test stage2, like just like normal Hello World. This is also kind of where I got my inspiration for the Hello World test for ARM, which is here. And this kind of gives you an overview of what stage2 is already capable of, because these are the things we already test for. Like I think Andrew's the main person working on the x86-64 backend. And yeah, these are the main things that are already supported on that backend. So people can just copy this code, try it out, and then for the incremental compilation, you have to use this watch flag. I think Andrew gives a wonderful intro to how to use the incremental compilation in the coding streams he has done. And that's also where I got my inspiration to do this. So yeah, I think he has multiple coding streams on working on this incremental compilation and working on SIG-IR and stuff.
Mm-hmm. You've been working on the code gen part for ARM. Have you taken a look at other parts of the self-hosted compiler, like how it does the parsing and how it produces IR, etc.?
Not so much, but I plan on checking out that, because I had a compiler course last semester, and yeah, I also want to see how it's also done like in real compilers.
Mm-hmm.
And yeah, but I haven't looked at that as much as the code gen part.
I see.
Yeah.
Well, sorry, this is just like a bit of curiosity about your university so, but how was the compiler course? Did they like teach you that you have to use Bison and Yak, or were they open to other possibilities?
So we had one compiler course which is mandatory for every student who wants to have the bachelor, which is an introduction to compilers. And I also chose the advanced compiler construction course, which is like not mandatory. And in the first one, we discussed things like basic parsing, ASTs, and basic codegen. And we used Java for that. So we built we built the tokenizers and parsers ourselves, and we didn't use a Yak or Bison. And yeah, I think it was like based on submissions, online submissions, and I don't think like it was really it had much room for creativity.
Mm-hmm.
But in the second course, it was more open and it was more focused on optimizations. And there you could like experiment with those optimizations yourself in some programming language. Yeah.
I see. Okay. There is one question. Is there a way to do different ARM code for specific targeted ARM versions? Like, can you do inline ARM for v7 and something else for v6?
This is about the inline ARM embedded in Zig code, right?
Let me see. I think.
Or
Is there a way to do different ARM code? That's a good question. I don't know if this is
like
for.
for the codegen itself, if you have like normal Zig code, I think I can demo this, which is already here. Let's search for V5. Oh. Yeah, for example, here, ARM CPUs older than V5 do not support the BLX instruction, which branches to a register and also at the same time saves our current position to the link register. Like CPUs older than V5 do not support that, and instead we can just do it manually. I plan to do this like more nicer instead of just embedding this into the codegen file. But for inline ARM, if you like want to switch on the ARM architecture and like switch if it has a V5, I think you can do that with conditional compilation. So at comp time, there will be the target is the target is comp time known. So you can have a comp time switch, and then if this target is done is correct, you can output this inline assembly. Otherwise, do this in inline assembly. So that would be a possibility.
Right. Let's see. I think there was a question. Oh, there was a question from way earlier, which mentions the leg VM. I've never heard of it, but so the question was: can ARM executables run on the leg VM? Have you ever heard of what it is?
No, I have not heard of that.
Okay, then I guess JKF SDA will have to give us more information. Otherwise, can't answer. Okay, that was awesome. I have another question though. I've seen that you have on Discord a Rocket logo and URL there. So, what's up with that?
In the first semester, we had a course which is introduction to functional and object-oriented programming languages. So, for the object-oriented part, we had Java, and for the functional part, we had Racket. And at the beginning, I was so confused by the Racket syntax and the parentheses and stuff, and I almost hated it. And then, as time went by, I began to realize that it's also a useful programming language, and it's it's also very useful for some stuff. And I then just shows that as a profile picture. Yeah.
I see.
Yeah.
Oh, apparently that was a joke. I'm sorry. I'm way too out of the loop to understand that joke. Okay. There's another question. Unrelated to the ARM backend, but more related to the new ARM MacBooks. How do you create universal binaries for both x86 and ARM inside? Can you?
Oof, so first of all, the new ARM MacBooks I think have ARM 64, so ARC 64. But I don't own a MacBook, and I don't know how that works specifically. But you could then use once the ARM 64 backend is complete, you could use that on a Mac. Also, I think the executable format for Macs, the Mach-O or Mac-O, is also in progress and is in the process of getting merged. And once that's finished, we should see support for ARM MacBooks coming soon.
That's great. Oh, by the way, there's also Jacob Kubcon in chat who is answering, who is the one working on
correct,
macro linking, right? So I said that also in the newsletter. I repeated on stream, guys. I really hope like by your powers combined, I will be able to use incremental compilation on the Mac when it comes out. So let's see the comments. For the record, for the people watching the video, so Jacob replied in chat that as far as he knows, it's FAT binaries on macOS, which pack both machine code for x86-64 and ARC-64, which is interesting. Because June says it's like a machine code Quine. I don't know. Well, I guess the packaging around the machine code itself can be OS dependent in any case, right? So it doesn't have to do strictly necessarily with the architecture. I'm guessing that's data that the OS can inspect and reason about. Anyway, Jacob says, blame me if something doesn't work. I will. Well, not blame, but I will open issues and ping you.
It's good that we have many architectures we support.
Yeah. Okay, that was awesome. Thank you very much. Is there anything else you want to say before we move to the second half?
At the moment, no, but I'll be happy to come again at Showtime with maybe a different topic. Let's see.
Absolutely. Absolutely. Yeah. I would love to have another talk from you. So thank you very much. And let's move into the break. So